Welcome to 1257 Swerve Overview. As always, here's our website if you want to access any of the resources mentioned here. Okay, so let's start with what Swerve actually is. Now, Swerve is a type of drivetrain which allows the robot to basically move in any direction it wants while spinning. So it consists of these four different modules, as you can see in this example, and they're positioned in the four corners of the robot to allow the robot to move. So these are what the individual Swerve modules look like. There's multiple different kinds of Swerve modules, and the basic idea is that one motor turns the wheel and the other one drives it. So you can have mechanically many different kinds of configurations of these motors and like gears to turn these things. So here you can see the motors are underneath. These are MK4Is, whereas these are Rev Max Swerve, and it's what our team uses. These wheels allow the robot to move in any direction by controlling the turn position as well as the speed at which the drive motor is driving. And so basically the robot moves in the direction that is the sum of all of these four different modules. So if all these modules point this way, the robot's also going to move this way. And then these are the things that you can control to change how the robot moves. Now, let's really quickly just watch these modules move um, in simulation. So here you can see the wheels are moving forward and back, and now they're moving side to side as well. You can see the modules rotate, and also the length of the length of the vectors, which represents the drive speed, also changing. Okay, so there's three different ways that our swerve drivetrain can move. It can move forward, it can also strafe, and it can also spin in place. Now, the way we control all these different kinds of motions is through a class called chassis speeds in WPILib that takes basically these three joystick inputs and converts them to speeds the robot can drive at. Okay, now let's look at how we convert these speeds to set points. So, for example, let's say we want our robot to go this way, right? Now there's a specified speed and angle associated with this set point. And so we want all the modules to have that angle and that speed as well. And so basically we take our chassis speeds and we convert them to something called swerve module states, which represents the state for each individual swerve motor. And so eventually, if you're doing a bunch of things together, this gets more complicated, but this is the basic idea. You take the chassis speeds for the general robot and convert them into four different ones for the swerve modules. And if you wanted to spin, for example, clockwise, the swerve modules would all have to point this way perpendicularly, and so that would allow the robot to spin. And just seeing everything put together, here's an example of the robot driving around. And so you can see the robot kind of take a curved path there. And as it's going back, like not all of these arrows have an equal length. And that basically allows the robot to turn like very slightly in a curved motion to get these uh, notes. And so the combination of going forward and turning is what allows our swerve drive to do these things. Another step in controlling our Swerve modules is the optimization step. There's an issue with directly setting our Swerve modules to the angles that we want it to. So, for example, let's say our wheel location is this, and this red line is our commanded speed. The wheel would have to turn a lot in order to get to that position. So this is not optimized. Turning this much wastes a lot of valuable time. And so the better way to do this, the optimized way, is to instead turn it a little bit, but reverse the direction that the wheel is pointed. So this is still the front of the wheel here, except instead of turning forward this way, it reverses and goes that way. And so this saves a lot of time and is what we call an optimized swerve module state. And so in our code, instead of just telling it to, hey, go at whatever this angle is, we use optimized swerve module states instead. Okay, now let's follow these set points. So in this example, red is where it's going, and then blue is its set point. So you can see here, it tracks it pretty well. It's not perfect, but it's enough to like accurately follow the joystick inputs here. And then autos follow a similar concept. So instead of the driver controlling the forward strafe and spinning joystick, It's basically given to a PID controller in auto that allows the robot to basically act, or the trajectory controller to act as the human driver. And so basically you can have it follow paths like these in auto, and that's what allows Swerve autonomouses to happen. That's all we wanted to cover in this episode. Stick around for the next one where we'll talk about how to program all of these things together.